There's a question that makes physicists squirm, not because it's complicated, because it's simple, devastatingly simple. How do you know your theories are actually true? Not useful, not accurate. True. Most scientists will give you careful answers about provisional knowledge and falsification. But Richard Feynman? He said something nobody expected. Something that changed how we think about science itself. The question goes like this. Every law of physics you've ever tested was tested in the past, at specific locations, under specific conditions, but you claim these laws apply everywhere, always, forever. You tested gravity here on Earth, maybe on the Moon, but what about a galaxy 10 billion light-years away? What about 5 minutes from now? You haven't checked. You're assuming. And that assumption has a name. Induction. The idea that the future will resemble the past. That patterns we've seen will continue. Here's the problem. You cannot prove induction is valid. Try it. Any proof you attempt will use evidence from the past to make claims about the future. You're assuming the very thing you're trying to prove. Philosopher David Hume showed this in the 1700s. He called it the problem of induction, and it undermines the entire foundation of science. If you can't justify induction, you can't justify any scientific claim that goes beyond direct observation. Most physicists, when cornered with this, retreat to pragmatism. They say science doesn't claim absolute truth. It builds models, makes predictions, tests them, revises when needed. All true. But then why do we talk about discovering laws? Why do textbooks say we've learned how the universe works? Why does it feel like we're uncovering truth rather than inventing useful fictions? Feynman saw this tension, and instead of dancing around it, he grabbed it with both hands. In a lecture at Cornell in 1964, he said something shocking. He said, "We have absolutely no reason to believe that the laws of physics are the same everywhere in the universe. None whatsoever. The only reason we assume they are is because it's the simplest assumption. And if that assumption ever fails, we'll just make a more complicated one that works." Let me repeat that. Feynman, one of the greatest physicists who ever lived, openly admitted that the universality of physical laws is an assumption we cannot justify. We use it because it works. The moment it stops working, we'll drop it. That's it. No deep philosophical foundation, no logical proof, just pragmatism. But here's where Feynman went further. He said the question, "Are the laws of physics true?" is asking the wrong thing entirely. You're treating scientific theories like they're descriptions of reality. Like there's a real universe out there doing things, and our equations are snapshots of that activity. Feynman flipped this. He said, maybe theories aren't descriptions at all. Maybe they're algorithms for making predictions. You input initial conditions, you run the algorithm, you get a predicted outcome. Then you check if that outcome matches what you observe. If it does, the algorithm is useful. If it doesn't, you need a better algorithm. In this picture, asking if a theory is true is like asking if a map is true. A map isn't true or false. It's accurate or inaccurate, useful or useless, detailed or simplified. The map is not the territory, and the theory is not the reality. This isn't just philosophy. It has practical consequences. In the 1940s, quantum electrodynamics was broken. The math gave infinite answers. Nonsense. Feynman developed a technique called renormalization to fix it. You calculate an infinite quantity, subtract another infinite quantity, and what remains is finite and matches experiments to 10 decimal places. Philosophically, this is absurd. Infinity minus infinity doesn't equal a finite number. It's undefined, meaningless, and yet it works perfectly. Feynman's reaction? Use it. The universe is telling us this is the right calculation. We don't need to understand why infinity minus infinity gives sensible answers. We just need to follow the recipe nature is showing us. Other physicists hated this. Paul Dirac called renormalization just a stopgap procedure. He thought there must be a deeper theory that avoids infinities altogether. Feynman agreed it was ugly, but he said ugly doesn't matter. What matters is whether it works, and it does. Quantum electrodynamics became the most precisely tested theory in history. We can calculate the magnetic moment of the electron to 12 decimal places, and experiments match. That's not truth, but it's something. Now watch what Feynman did with quantum mechanics itself. The standard approach, developed by Schrödinger and Heisenberg, uses wave functions. You solve an equation. The wave function spreads out. You make a measurement. It collapses. This works, but it's conceptually bizarre. What is a wave function? Where does it exist? What does it mean for it to collapse? Feynman invented a completely different way to do quantum mechanics. The path integral formulation. He said, forget about wave functions. Instead, imagine a particle traveling from point A to point B. In classical physics, it takes one path, the path that minimizes action. In quantum mechanics, Feynman said the particle takes every possible path simultaneously. Straight lines, curved paths, loops, paths that go backward in time. Every path you can imagine, no matter how absurd, contributes to the final probability. You assign each path a number called an amplitude. You add all the amplitudes together using specific rules. And out pops the same answer you'd get from Schrödinger's wave function. Same predictions. Completely different picture, so which one is right? Feynman's answer revolutionized how we think about this question. Neither is right. Both are right. They're different languages for describing the same physics, like describing a landscape in English versus French. The landscape doesn't care which language you use, it's still the same landscape. This is profound. It means physical theories are not unique. Multiple incompatible-looking theories can describe the same reality equally well. And this tells us something crucial. The theory is not the reality. Reality is whatever underlying structure makes both theories work. We don't have direct access to that structure. We only have our theories, our maps, our algorithms, and none of them are the final word. Feynman loved this. He loved having multiple ways to think about the same physics. In his lectures, he'd solve the same problem 3 different ways. Particles, waves, fields. Each perspective revealed something the others hid. And he'd tell students explicitly, don't ask which perspective is correct. They're all correct. Use whichever one makes the problem easier. Let me give you a concrete example. The double-slit experiment. You shoot electrons one at a time through 2 slits. They build up an interference pattern on the screen behind. Wave-like behavior. But if you measure which slit each electron goes through, the interference disappears. Particle-like behavior. Standard quantum mechanics explains this with wave function collapse. Feynman's path integral explains it with destructive interference between paths. Both get the same answer. Both are equally valid. Neither tells you what's really happening, because that question assumes there's a unique story to tell. Feynman gave a lecture in 1963 where he said something even more radical. He said, nobody understands quantum mechanics. Not him. Not anyone. You can learn the rules. You can do calculations. You can make predictions. But understanding, in the sense of having an intuitive picture that matches everyday experience, that's impossible. And it's impossible for a reason. The quantum world doesn't work like the everyday world. Your brain evolved to understand rocks and trees and predators, not electrons. Expecting quantum mechanics to make intuitive sense is like expecting a fish to understand bicycles. This drove other physicists crazy. Einstein famously said, God does not play dice. He thought quantum mechanics was incomplete. There must be hidden variables, deeper explanations that restore determinism and common sense. Feynman's response was blunt. Nature doesn't care what you want. Nature doesn't care what makes sense to you. Your job is to figure out how nature actually behaves, not how you wish it behaved. The test came in the 1980s. John Bell proved that if hidden variables exist, they must violate something called locality. Information would have to travel faster than light. Experiments confirmed Bell's prediction. Quantum mechanics is genuinely weird. There are no hidden variables making everything deterministic behind the scenes. Feynman was right. You don't get to demand that nature be intuitive. Now here's where Feynman's philosophy gets really powerful. If theories are just algorithms for prediction, then you can invent wild, crazy theories and see if they work. You're not constrained by what makes sense. You're only constrained by what matches experiment. This freed Feynman to think in ways other physicists couldn't. In 1948, he developed Feynman diagrams, little pictures showing particles moving through space and time, interacting, splitting, combining. Other physicists thought they were just mnemonics, memory aids for keeping track of calculations. But Feynman showed each diagram corresponds to a term in the mathematical calculation. You draw all possible diagrams, you convert each one to a number, you add them up, and you get the probability of a physical process happening. This sounds simple now, but at the time it was revolutionary. The standard way to calculate particle interactions involved pages of complex algebra. Feynman diagrams reduced it to drawing pictures. A week's worth of calculations became an afternoon. And more importantly, the diagrams suggested new physics. You could draw diagrams representing processes nobody had thought to calculate before. Virtual particles popping in and out of existence. Particles traveling backward in time, which Feynman reinterpreted as antiparticles traveling forward. The method itself generated predictions. Are Feynman diagrams real? Do virtual particles actually exist? Feynman would say you're asking the wrong question. The diagrams are a calculational tool. They work. That's what matters. If you want to imagine them as representing real processes, fine. If you want to treat them as pure mathematics, also fine. The universe doesn't care about your interpretation. This brings us to something Feynman cared deeply about. The difference between knowing the name of something and knowing something. He told a story about his father taking him for walks in the woods. Other kids would say, "That's a brown-throated thrush," and think they knew something. Feynman's father taught him differently. He'd say, "You can know the name of that bird in every language in the world, and when you're finished, you'll know absolutely nothing about the bird. You'll only know about humans in different places and what they call the bird." Feynman applied this to physics. Students would memorize definitions. Energy is the capacity to do work. Momentum is mass times velocity. They'd pass tests, but they didn't understand. Real understanding meant being able to solve new problems, to apply concepts in unfamiliar situations, to see connections between different areas of physics. That required thinking, not memorizing. He was brutal about this in his teaching. At Caltech, he gave lectures that became famous, later published as the Feynman Lectures on Physics. He'd start with simple questions. Why are balls round? Then he'd dig deeper, and deeper, until you were thinking about molecular forces and energy minimization and symmetry. He never let students get away with surface answers. He pushed them to think about what's really happening. But here's the paradox. Feynman also said, we never know what's really happening. We only know our models. So what does it mean to understand physics? It means being able to use multiple models, to translate between them, to know when each one is useful and when it breaks down, to hold them all lightly, knowing they're provisional. In 1959, Feynman gave a lecture called "There's Plenty of Room at the Bottom." He talked about manipulating individual atoms, building machines at the nanoscale. Everyone thought it was science fiction. But Feynman's point was deeper. He said the laws of physics, as far as we know them, don't forbid this. We can't see any fundamental obstacle. Therefore, we should explore. We should try. We should see what's possible. This became the foundation of nanotechnology. Not because Feynman proved it would work, because he showed there was no proof it wouldn't work. And in science, that's enough to start experimenting. You don't wait for certainty. You follow possibility. Feynman did this throughout his career. He worked on the Manhattan Project, helping build the atomic bomb. He investigated the Challenger disaster, demonstrating with a glass of ice water and a rubber O-ring exactly what went wrong. He contributed to particle physics, to quantum computing, to biology. He was everywhere, and in every field his approach was the same. Question assumptions, test ideas, follow evidence, don't get attached to theories. Let me tell you about his Nobel Prize. In 1965, Feynman won for quantum electrodynamics. He shared it with Julian Schwinger and Shinichiro Tominaga. All three had developed the same theory independently, but their approaches looked completely different. Schwinger used operator algebra. Tominaga used relativistic quantum field theory. Feynman used path integrals and diagrams. Mathematically, they were equivalent, but conceptually, they seemed unrelated. What does this tell you? It tells you the theory exists independent of any particular formulation. There's some structure in nature that all three approaches are capturing, but none of them are that structure. They're different roads to the same destination, and the destination is accurate predictions, not ultimate truth. Feynman's Nobel lecture was unusual. Most laureates use the opportunity to explain their work in detail. Feynman spent half his lecture talking about the history of quantum mechanics, about false starts and confusions, about how the theory developed through trial and error, not logical deduction. He wanted people to understand that science is messy, that it's not a straight line from hypothesis to truth, that it's full of wrong turns and lucky guesses and ideas that worked for reasons nobody understood at the time. Now, let's address the elephant in the room. If we don't know our theories are true, if they're all provisional and subject to revision, then what are we actually doing? Are we just making up stories? Is science no better than mythology? Feynman had a clear answer. No, because myths don't make testable predictions. Myths aren't constrained by reality. You can believe whatever you want about myths. But physics has to match experiment, and experiments are brutal. They don't care about elegance or intuition or how much sense a theory makes. They only care about accurate predictions. This is the constraint that makes science work. You can invent any theory you like, but nature gets to vote. And if your theory predicts that dropped objects fall upward, nature votes no. Immediately, decisively. Your theory is dead. This is completely different from other human endeavors. In art, in philosophy, in politics, you can argue forever about what's correct. But in physics, there's a referee, the universe itself, and its judgment is final. Feynman called this the key to science, the idea that you can be wrong, that there are experiments that could prove you wrong, and that you actively look for those experiments instead of avoiding them. Most people, when they have a belief, they look for evidence supporting it. They ignore evidence against it. They rationalize contradictions. Scientists are supposed to do the opposite, supposed to try to destroy their own theories, to find the places where they fail. Did Feynman always live up to this ideal? No, he was human. He had intuitions he trusted, ideas he favored. But he was aware of the danger. He warned against it. In his famous Caltech commencement speech in 1974, he talked about cargo cult science. Scientists going through the motions of research without the essential ingredient, the willingness to doubt themselves, to question their assumptions, to admit when they're wrong. He said the first principle is that you must not fool yourself, and you are the easiest person to fool. This is hard. It goes against every instinct. Your brain wants to be right, wants to defend its beliefs, wants to ignore contradictory evidence. Scientific integrity means fighting that instinct, means leaning into uncertainty instead of away from it. So here's what Feynman showed us. The question, are the laws of physics true, misunderstands what science is. Science isn't a collection of eternal truths, it's a process, a method for testing ideas against reality. And the ideas that survive that testing are useful. Incredibly, miraculously useful. They let us build technologies, make predictions, understand phenomena that would otherwise be incomprehensible. That's not proof they're true. It's evidence they're capturing something real, some pattern in nature that exists whether we understand it or not, and we keep refining our understanding, making better theories, finding edge cases where the old theories fail, expanding our knowledge into new domains. This is what Feynman meant when he said the pleasure is in the finding out, not in having found out. The joy of science isn't knowing the answer, it's the process of discovery, the moment when you do an experiment and nature surprises you, when something doesn't work the way you expected and you realize you've been thinking about it wrong, when you see a connection nobody saw before and suddenly disparate phenomena fit together. Feynman experienced this over and over. When he developed the path integral, he wasn't sure it would work. He tried it. It worked. That moment of discovery, of finding out that this crazy idea actually describes nature, that's what drove him. Not the awards, not the recognition, the pure intellectual thrill of understanding something new. And he was honest about what he didn't understand. In his lectures on gravitation, he admitted openly that he didn't know why gravity exists. He could describe how it works, he could calculate its effects. But why mass causes space-time to curve? No idea. And he was fine with that. You don't need to understand everything to make progress. You just need to understand enough to ask the next question. The one question physics is afraid to answer is this: do we really know anything? And Feynman wasn't afraid. He said, no, we don't have certainty. We have evidence. We have theories that work. We have predictions that match observations to extraordinary precision. We have a method for testing ideas and discarding the ones that fail. That's not knowledge in some absolute philosophical sense. But it's something better. It's a living, growing, self-correcting process that brings us closer to understanding how nature operates. The universe doesn't owe us understanding. It doesn't owe us intuition. It doesn't owe us comfort or certainty or answers that make sense. What it gives us instead is consistency, patterns we can discover, regularities we can test, and the astonishing fact that simple mathematical laws describe vast swathes of reality with stunning accuracy. Feynman saw this as miraculous, not in a religious sense, in a profound, humbling sense, that we tiny creatures, evolved to hunt and gather on an African savanna, can nevertheless work out the rules governing everything from atoms to galaxies. That our minds, shaped by evolution for survival, can grasp the structure of space-time itself. That's not something we had any right to expect. But here we are, doing it. So when someone asks you how we know the laws of physics are true, remember Feynman's answer. We don't. We know they work. We know they've survived every test we've thrown at them. We know they've led to discoveries and technologies nobody imagined. We know they've revealed a universe stranger and more beautiful than anyone expected. That's not truth, but it's the best we can do. And it's enough. More than enough. It's everything we need to keep exploring, keep discovering, keep pushing at the edges of human understanding. Not with certainty, but with curiosity, with honesty, and with the courage to follow evidence wherever it leads, even when it takes us somewhere we never expected to go.